project aims to expedite vehicle removal following accidents. According to the Road Traffic Safety and Enforcement Seminar, the time from an accident's occurrence to police arrival accounts for about 30% of clearance time, with traffic congestion worsening exponentially due to supply-demand imbalances. Therefore, we proposed a pipeline that enables anyone in the car accident the ability to record the scene. People can reconstruct the scene simply by recording it with their cell phone. In this way, we can significantly reduce the time required, thereby alleviating traffic congestion. This plot shows the overall workflow for our project. We start by recording a video, then apply a Laplacian operator threshold to filter out any blurry images. Using Colmap, we then determine the camera positions and generate point clouds. With this setup, our proposed Gaussian splatting model is used to train the scene. Finally, we can either use SSH port forwarding to open a visor viewer on the client side or export the mesh on the server side and download it locally. Recently, 2D Gaussian splatting has emerged as an effective method for view-consistent radiance field. The author discovered that the volumetric nature of 3D Gaussian splatting results in difficult mesh reconstruction. Therefore, they propose Surfel splatting, which distributes volume density across a planar disk rather than a 3D blob, creating view-consistent geometry while inherently modeling surfaces. The 2D Gaussian splats are then projected into the object space. 2D Gaussian splatting performs well in most scenes, however it struggles with high light environments which frequently occur in automotive settings due to reflections from the car body. As shown in the image, both the surface normal and the mesh reveal a significant hole in the center of the metal sheet, which is an outcome we want to avoid. So, why is this happening? We believe this outcome is due to reflections. Consider this example. We have an observer and an object. The object forms a virtual image in the mirror, which behaves just like a distant object as the observer moves. Therefore, attempting to synthesize the geometry without accounting for reflections inevitably leads to a dual-layered structure. In this structure, the surface contains a hole in the center, allowing the background or virtual images to appear in the final render. To solve the problem, we proposed a three-stage strategy with deferred reflection. In the first stage, we established the basic structure, base color, and reflection strength of our model. In the second and third stages, we trained the environment map and reflection color. In the final stage, we introduced the lambda normal loss, as proposed by 2D Gaussian splatting, to ensure a smooth surface. Deferred reflection strategy involves training the foundational structure first, and then applying the reflection color afterward. Shown above, a Gaussian splatting pass is first performed to bake reflection strength, normal, and base color to screen space maps. In the following shading pass, for each pixel, a normal map is used to compute a reflection direction and query an environment map for a reflected color. The reflection strength is then used to blend base color and reflection color into the final result through interpolation. An image loss and lambda normal loss is used to backpropagate gradients. By leveraging the advantages of 2D Gaussian splats and the deferred reflection training strategy, we successfully generate novel view synthesis with a high-quality mesh. And here is the result. As shown in the normal map, we successfully filled the holes caused by reflections, demonstrating significant improvement compared to 2D GS. As demonstrated, the mesh extraction works well after adopting the 2D Gaussian model, along with their rasterization method and deferred reflection training strategy. Once the mesh is completed, we can proceed to the final step, calculating distances within the scene. Using applications like MeshLab, we can easily calculate distances based on known measurements. For example, we found the dimensions of the reconstructed car model, Lexus RX 450h, online. By using the car's length as a reference, we calculated the scale ratio between the model and reality. With this ratio, we determined distances within our mesh and assessed the error rate. As shown above, the error rates are below 10%, demonstrating that the proposed model can generate accurate meshes suitable for accident scene scanning. That's the end of the introduction to our projects. Accident Scene Optimization. Enhanced scene scanning with Gaussian splatting for swift vehicle clearance. Thank you for your attention.